its electrode assembly. The cathode's a piece of platinum wire. The anode's a carbon rod. It's dipped into the molten lead bromide. We connect up to the electricity supply. A current flows. The molten lead bromide does conduct electricity. What happens is this. At the cathode, the negative electrode, lead ions each pick up 2 electrons, forming metallic lead. At the anode, the positive electrode, for each lead ion discharged at the cathode, 2 bromide ions each give up an electron, forming elementary bromine. As the electrolysis proceeds, we can see red bromine vapour coming off from the electrolyte. After 15 minutes or so, quite a lot of liquid bromine has condensed out. The passage of electric current has split up the lead bromide into bromine and lead. You can see the pool of molten lead at the bottom of the tube. Here, in one department of the Mond division of ICI at Runcorn, they're electrolysing not lead bromide, but molten salt, sodium chloride. These are down cells for the production of metallic sodium. This is how they work. There's a steel pot with a brick lining. This contains a melted mixture of salt and calcium chloride at about 600 degrees C. There's a graphite anode, actually a clump of 4 like this in each cell. The anodes are surrounded by a steel cathode. This is a cross-section. When the electrodes are connected to the power supply, chlorine gas is liberated around the anodes. This is what happens. Because the anode is positively charged, it attracts the negative chloride ions. Each chloride ion gives up an electron to the anode and chlorine gas is produced. The gas bubbles upwards and is collected in a trap called the bell, made of nickel, and is piped off and used. At the cathode, metallic sodium is liberated. The negative cathode attracts positive sodium ions. Each ion picks up an electron, giving sodium metal. The sodium metal floats upwards and it too is collected. It passes over into a collecting vessel. In between the electrodes, there's a diaphragm made of steel mesh, which prevents the sodium from mixing with the chlorine and turning back into salt. Here are down cells in action. The flashes are caused by a little sodium escaping and burning in the air. The electrolyte contains calcium chloride as well as salt to lower the melting point. So calcium metal is also produced, but this solidifies in the pipe just above the cell and can be pushed back in. The sodium collects in the containers at the side. It's kept molten by gas burners underneath. Every 2 months or so, the diaphragm has to be changed in a cell. This is a very spectacular process. There's the bell which collects the chlorine. Here's the sodium container being removed. You'll see bits of blazing sodium dropping out of it. Now out comes the old diaphragm. You can see how it's been damaged. The current is still on and the electrolysis is still proceeding in the cell. Here comes a new diaphragm. You can see that there are 4 cylinders of mesh to fit over the clump of 4 anodes in the cell. The diaphragm's lowered into the cell so that collection of sodium and chlorine can be started again from this cell. Components removed from a cell are baked to burn off any sodium remaining in them, then sprayed with water, taking full precautions just to make sure. Sodium reacts violently with water, of course. They threw a lump in just to remind us. Beneath the cell room, ingots of sodium are cast from the molten metal. Sodium melts at 98 degrees C. It quickly solidifies in the molds. Sodium metal can be transported in other ways. This rail tanker is filled with sodium. It's going to a plant where the important metal titanium is manufactured. The sodium in the tanker is heated so that the metal melts. Then the gas nitrogen is used to blow out the liquid sodium. They're coupling up the nitrogen hose. The nitrogen forces the sodium along pipes to big storage vessels where it's kept liquid until it's used. Each of these containers holds hundreds of kilograms of molten sodium. It'll be used to make titanium. This is finely divided titanium metal. Titanium is a very reactive element. Watch what happens when a pile of the granules is ignited in air using an electrical heating element. It burns very fiercely indeed. The oxides formed are beautifully coloured. This is typical of the transitional elements, of which titanium is one. Because titanium is very reactive, we must use an even more reactive element to win it from its compounds. This is where the sodium comes in. Because it's even more reactive than titanium, it'll remove the chlorine from titanium 4 chloride, leaving titanium metal and sodium chloride. The more reactive element replaces the other. Here's one of the steel vessels in which that reaction is carried out. It's lowered into a brick-lined oven, which can be heated up to a high temperature by gas burners. The air inside the vessel is replaced by the noble gas argon. Then the liquid sodium is run in. The little gas jets keep the sodium molten. When the sodium's in, the pipe's disconnected, and then liquid titanium 4 chloride is added down this pipe. Now the reaction vessel's heated for 36 hours. It's allowed to cool, then opened. Inside, there's solid salt, sodium chloride, coloured by the presence of traces of titanium compounds, and dark-coloured titanium metal. The salt's dissolved in water, and the titanium is filtered off and dried. Then it's packed for delivery to customers. One use for titanium is for making the turbine blades of jet engines for aircraft. Another is for making artificial joints. This is a titanium hip joint. There's a whole group of metals like sodium, all of which are reactive. Let's look at them. We'll start with sodium. It's stored in oil to prevent it oxidizing in the air. It doesn't look like a metal. It's soft. But when you cut it, you can see the metallic luster for a moment before white sodium oxide forms on the surface and dulls it. Lithium has a lower atomic mass than sodium. It's not quite so reactive. It's harder to cut, but once again the gleaming surface quite quickly changes as the metal is oxidized in air. Potassium has a higher atomic mass number than sodium, and it's even more reactive. Again, it's stored in oil. Watch. Rubidium is a very scarce element of even higher atomic mass number, and it's even more reactive than potassium. It has to be kept in a sealed, evacuated container. It reacts immediately with the oxygen in the air. You may be able to see little red-hot sparks as it burns. Cesium is even scarcer with a still higher atomic mass number, and it's the most reactive of all metals. It melts at body temperature, as you can see. The warmth of your hands will melt it. It oxidizes as soon as it gets in contact with air and stays molten with the heat of the reaction. All these metals react vigorously with water, and hydrogen is given off. This is lithium again, the least reactive. It never gets hot enough to ignite or explode. The alkali lithium hydroxide is also formed. All these metals form alkalis with water, and they're called the alkali metals. Sodium reacts more vigorously with water, but a small piece like this may not ignite, not like that bigger lump we saw earlier. Potassium always ignites because of the heat given off in the reaction. We can only use a tiny portion of rubidium, it's so expensive, but you can see how vigorously it reacts. And cesium's the most reactive of the lot, remember. What about that other very important product from salt, chlorine? In the ICI Mons division, it's used to make a whole variety of useful substances. Just one example, solvents. The chlorine reacts with hydrocarbons to produce a whole range of industrial solvents. These are the distillation columns for separating them out. Remember the mercury cells making chlorine and alkali and all the electrical energy they use up? Well, it's worth doing, largely because of the great usefulness of chlorine. Chlorine is one of a group containing the most reactive of the non-metallic elements, the halogens. Watch what happens when it comes into contact with a compound of another, less reactive member of the group, iodine. Once again, a more reactive element replaces a less reactive one. Dark-coloured iodine is liberated. Here's the equation for the reaction. Chlorine is more reactive than iodine and displaces it. Now there's another halogen even more reactive than chlorine, fluorine, produced by electrolyzing melted fluorides in a special cell. It's very dangerously corrosive because of its reactivity. Look what happens when a strip of paper soaked in potassium iodide solution is exposed to this gas. Iodine is liberated as before, but so much heat's produced that the paper ignites. The equation. Fluorine's even more reactive. It displaces the iodine and, as you saw, produces a great deal of heat. This is a hydrocarbon called toluene. It's inflammable. Let's see what happens if we pass chlorine gas over it. Nothing. But with fluorine, a reaction vigorous enough to set light to the toluene. Here's another demonstration of the very great reactivity of fluorine. We take some of the noble gas xenon and pass it into a perfectly clean, dry, evacuated glass vessel. We fill an upper part of the apparatus with fluorine. Then we allow the two gases to mix together. We leave the apparatus in daylight for some hours. After several hours, there are crystals inside. Fluorine is so very reactive that it has even formed a compound with a noble gas, xenon fluoride. But industrially, the really important material is that compound of the alkali metal sodium with the halogen chlorine, common salt, sodium chloride, NaCl. One important source of salt is the Great Cheshire salt field in northwest England. In these two films, we've seen just some of the uses to which it's put in the chemical industry today.